morning. And now let's continue by this quick revision of algebra. So hopefully today it will be finished, and then I can even assign you your first homework, right? So we talked about how we want to do the multiplication of matrices or the conditions. Then we talked about the norm, the second norm, basically Euclidean norm. And we said later we will learn the different type of norms. And one of the important things that we had in matrices and in algebra before was the determinant of a matrix. The determinant of a square matrix A belongs to R n by n is, now we were defining the determinant by this. We show it as a det A, or we were putting the absolute sign, and it is equal to j 1 to n, and the summation of j from 1 to n, aij minus 1 to the power of I plus j, determinant of aij, where determinant of aij is the determinant of a matrix, an S-square matrix, and n minus 1 by n minus 1 matrix obtained by ignoring the ith row and j's column of A. You may remember a few famous determinants, like for example, if A is 1, 2, 3, 4, then the determinant of A, it was 1 multiplied by 4 minus 2 multiplied by 3, which was minus 2. And if you have a 3 by 3 matrix, you remember that you were solving it like 1, 2, 1, 0, minus 1, minus 1, 2, 3, 0, and then the determinant was calculated by, if you use the formula, it is equal to, let's first take this one, which is A1 and 1, so it's 1 multiplied by minus 1 to the power of 1 plus 1 multiplied by the determinant of, I ignore row 1, column 1, column 1, row 1, and what is left is the determinant of minus 1, 3, 0. Unfortunately, the red is dead. Plus, then we consider the second one, 2 multiplied by minus 1 to the power of row 1, column 2, the determinant of, now I'm ignoring row 1, column 2, it's 0, minus 1, 2, 0, plus, and I'm picking the last one, 1 multiplied by minus 1 to the power of first row, third column, determinant of, now I am ignoring the first row, third column, what is left is this matrix, which is 0, minus 1, 2, 3. So it will be equal to, this is 1, and this result is basically 3. This one is minus 1, this is minus 2, and this result is 2, so minus 2 multiplied by 2 is minus 4. And then this is 1 multiplied by 2. So the result is 1. So the determinant of this matrix is 1. This was how you used to calculate it. Of course, in this course you can have your calculator, you have your computer. If you need to calculate the determinant, you just simply calculate it by that. The reason that we did it was that maybe we have a parametric matrix and we need to calculate the determinant of the parametric matrix. Now, and if you also remember, there have been some very important properties that these matrices had, this determinant had, and let's go over these properties. Because if we want to prove something and come to some conclusion, we need to benefit from these properties. I'm erasing. If I write fast or erase quickly, just let me know and I wait, okay? Do we have any question regarding to this? Okay, cool. So we continue. Which one is right? So some properties. Changing rows, changing a row with another row will, if you have the matrix and if you just change these two rows or change these two columns, what will happen?
Multiplied by minus 1.
Yeah, only the sign of the determinant, excellent, will be changed. Only the sign of the determinant will be changed. Second one, adding a row with another row will, if we are adding one of the rows to another row and then we calculate the determinant, or one of the column to another column and then we calculate the determinant, what will happen to the determinant? Yeah, the determinant, very good, will not change. It will be the same value as it was. If two rows of a matrix are the same, the determinant will be 0. So this can be actually written in a more general form if a row is result of linear combination of other rows, then the determinant is 0. So actually, if one row is like a linear combination of other rows, then the determinant will be 0. Like assume that this row was 2i of this row plus minus 1/3 of this row. Then the determinant will be 0. Now, the determinant 0 is quite important for us, because if the determinant is 0, we call the matrix with a special name. If determinant of A is equal to 0, then A is called to be singular. Now, till now, in the undergraduate level, when we come to the matrix which is singular, we stop by and then we said, oh, we cannot handle this. Now in this course, in the reality, we will see that how we can handle the singular matrices. Okay? Let's have a few more properties. If we have A and B, then determinant of AB is the determinant of A multiplied by the determinant of B, which is equal to determinant of BA. If AB exists, does BA also exist?
Yeah.
Yes, because we understand that this is a square matrix and you can really interchange the multiplication. The results are not necessarily the same, but the determinants are the same. Fifth one, if we multiply a row with a constant k, then what can we say about the determinant?
We multiply the determinant with the constant.
We multiply the determinant with a constant. If we multiply all rows and columns with a constant, in other words, if now we have all the matrix multiplied by k, it will be, listen, if we multiply one row, we said that we just multiply the determinant with one constant. What will happen if I multiply a whole matrix with a constant?
Nothing.
How come? If you multiply one row, you just said that the determinant will be multiplied by k. Now, what will happen if I multiply the whole rows? Well, let's come to the results together. If I multiply one row, it will be k times. How many rows do I have? N. So it means that k multiplied by k multiplied by k, how many times? N times. So it will be k to the power n determinant of A. Because if I multiply only one row or column, it will be k determinant of A. Now, it's like that I am multiplying each row with k, and I have n of these values. So it will be k multiplied by k multiplied by k for n times. So it's k to the power n. So if the determinant is 0, it's called singular. Now, again, in undergrad algebra, or in most algebra classes that you have taken here, the next thing that they were saying was, okay, we have the determinant, we use the determinant to say that if a matrix is singular or not, and then they said that if a square matrix is non-singular. What does it mean, non-singular?
The determinant is not 0.
The determinant is not 0 and it exists, of course, obviously. Then there exists a multiplied by a to the power minus 1, which is equal to a to the power minus 1 multiplied by a, which is equal to identity, and it's very sad that this is not, I think. And a to the power minus 1 is called, what does it call?
Inverse.
Inverse of a. So look how many conditions we have here. S square matrix, it is non-singular, then we can calculate the inverse. You are coming to computer science, right? You do pattern recognition, you do image processing, you do I don't know, big data handling, and inside your image you calculate, you see that, oh, first thing, it's not S square, and somehow you need to find its inverse. Or you see that, oh, you have huge data, and it happened that some of the rows are linearly depending the other ones, so the determinant is 0, but you need to find the inverse. And because of so many constraints that we have, the inverse is not defined, whereas we need to calculate some other inverse. That's why in this course we will talk about how we can handle calculation of the inverse of a matrix which is not a square, calculation of the inverse of a matrix which is singular. Okay? But we will talk about it after we finish the revision. Now the inverse has had a few properties. The first property, I don't know if you remember it or not. A multiplied by B, if the multiplication is valid, A multiplied by B inverse is equal to
B inverse times A inverse.
B inverse times A inverse. Noting that A and B are S square matrices. Okay? Noting that A and B are S square matrices, because A multiplied by B can be an S square, not necessarily A and B are S square. For instance, A can be n by 1, B can be y by n, and the result is n by n. So we are assuming that A and B are S square matrices. We said if we have, if we multiply a matrix with k, all the rows or all the columns by k, in other words, if we are multiplying a matrix by k, the determinant will be like k to the power n. What will happen to the inverse if I am multiplying my matrix with a constant k?
K minus 1 times.
Yeah, I mean, it will be like same rules that we have here, right? A inverse multiplied by k inverse is 1 over k, right? And it's a constant, so we can write it before after. K is just a constant. which is not 0, obviously. And the third one is easy one. Inverse of an inverse is itself. Inverse of an inverse is itself. If determinant, well, I cannot say if the determinant of A exists. Why? Because I'm talking about the inverse of a matrix. Definitely the determinant exists. So, what is the determinant of A inverse? We can actually easily see what it is by using the first property and knowing the definition of the inverse. A inverse, we said it is I, right? So the determinant of A inverse is the determinant of A multiplied by the determinant of A inverse multiplied by the determinant of I, which we know that the determinant of I is 1. So the determinant of A multiplied by the determinant of A inverse is 1, so we come to the conclusion that the determinant of A inverse is 1 over the determinant of A. The next property was actually determinant of A multiplied by A inverse is 1. And A inverse is calculated by 1 over A multiplied by adjoint of A what is adjoint of A? Adjoint of A is a matrix which is simply obtained by ignoring the i's and j's columns of a matrix. But for us it is important to quickly know if we have A is A11, A12, A21, A22, then A inverse is, what is A inverse? It is 1 over the determinant of A, which was 1AA, A11, A22, minus A12, A21, multiplying by elements of main diagonal of switch, and elements on the off diagonal are kept, but the sign is changed. We know that, for example, the adjoint for this element is obtained by ignoring the first column and the first row. What is left is this one by itself. Now, what we want to do now is we want to talk about something very important. We talked about you did not have it in your undergrad algebra. Still, we are sticking with the known or standard type of matrices, and but there are some formulas. We will prove a few of them together. You need to know them because we want to use the consequences of them. In other words, we want to know just the results, and you always have these ones in front of yourself. And it is this concept. Sometimes, again, especially in computer science, this is very useful. We are having sometimes huge matrices, right? We have huge matrices, and we want to, let's say, calculate its determinant, or maybe we want to calculate its inverse, and so on. So handling a huge matrix is not easy. But for instance, handling a 2 by 2 matrix is easy. So imagine that I have a 4 by 4 matrix and I want to find its inverse. If somehow I can divide it into 2 by 2 matrices, then I know how to handle each of those parts, if I know how to handle the relationship between those things. In other words, we want to see what will happen if I have a matrix which has blocks inside it. And by block, I mean a matrix. So in other words, we have a matrix which is huge, but each part of it can be a matrix by itself. Not necessarily these matrices should have the same size, but we can have different blocks. So we want to talk about block matrices. Given A to be a matrix of, and let's call it of n by n, B be a matrix of n by m, C be a matrix of n by n, B was n by m, and D be a square matrix of m by m. A block matrix is defined to be matrix of matrices like this. Which the size is n plus m by n plus m. Then we have, if you have a matrix, a block matrix like A, 0, C, D, or A, B, 0, D, the determinant is determinant of A multiplied by the determinant of D. Obviously, if A or D or both of them is singular, then the determinant of A0CD or AB0D is equal to 0, because if determinant of A or determinant of D is 0, if determinant of A is not a 0, then the full block matrix ABCD is determinant of A multiplied by determinant of D minus cap C A inverse B. And this matrix D minus C A inverse B is famous. It's called sure complement of A if determinant of D is not 0, then the same determinant can be calculated as determinant of D multiplied by determinant of A minus B D inverse C, and A minus B D inverse C is sure complement of D. And it is because
Question. Is it then also true that if both are non-zero, then the sure complement of...
But you can either write it in this form or this form. This is because of this sentence that I will write. The black matrix, which we have described a few minutes ago, can be written as, now this matrix A, B, this black matrix A, B, C, D can be actually written as CA inverse, and the main diagonals are all 1, multiplied by A, B, 0, D minus CA inverse B. Or it can be written as I B D inverse 0I multiplied by A minus B D inverse C 0 C D. I think you can find the proofing of this type of decomposition on the internet, but you know that if we have multiplication of two matrices, matrix A multiplied by matrix B, the determinant is determinant of A multiplied by determinant of B. So in other words, this determinant is determinant of this multiplied by the determinant of this. This determinant, it's a lower triangular matrix, which means that only multiplication of elements are main diagonal, which is all 1. So this is 1. And this determinant, this is upper triangular matrix, again multiplication of the main elements, which is this determinant multiplied by this determinant. And this formula is proven if we write the decomposition in this form. This is an upper triangular matrix. The determinant is multiplication of main elements, which is determinant of I multiplied by determinant of I, which is 1. Multiplied by this lower triangular matrix, which is the multiplication of the main diagonal, which means determinant of A minus B D inverse C multiplied by determinant of D, which is here. Now, question is that if determinant of A is not 0, determinant of B is not 0, which of these ones do I have to use? Which of these ones is easier to calculate? You will use that one. Remember, sometimes it will be maybe useful, we will talk about what will happen if the matrix that we have is not a square matrix, then we will see how we can calculate the inverse. All these formulas will be correct, but sometimes we have huge blocks, and this block might be a diagonal. Easily we can calculate some value. This is one scalar, which we know its inverse is just 1 over that one. And these ones are vectors, and we will learn how to find the inverse of a vector. So it will be easy for us to manipulate this type of matrix than the whole matrix as itself. Again, in probability theory, which we will talk about them in next semester, we see that this type of matrices, this type of divisional matrices is very useful because each part has a special meaning about prediction. Okay, we don't talk about them now. And if the determinant of A and the determinant of D is not 0, then, so if the determinant of A and D are not 0, what can we conclude?
This block matrix is not singular.
It's not singular because we know if one of them is 0, it's singular. So if they are not 0, it's not singular, it's non-singular. And if it is non-singular, it means
As an inverse.
we can calculate the inverse. So let's see what is the inverse. Then we can calculate the inverse of A0CD. And we can calculate the inverse of AB0D. The first one, it will be A inverse 0 minus D inverse CD inverse, CA inverse, multiplied by, and in the next element is D inverse. Or in here we have A inverse minus A inverse B D inverse, and this is the D inverse. So this is the inverse of these two matrices. Again, we don't care about the proof, but it's quite a very handy formula to know. Now, if we have numbers, as I said, we have computers in front of ourselves. The computer will calculate it. Why we need to know these things? If we have a parametric matrix, which is very useful if we are doing some research. Usually we are ending up with some parametric matrices which need to be handled. So knowing these formulas or consequences is very essential for us.